seems like my Apple laptop didn't work with the presentation. But anyway, now that we're started, hi, I'm Dheevatsa. I'm from the AI software co-design team. And I'm going to be talking about the hardware software co-design for future AI platforms at Facebook, and particularly looking at our next generation training platform, which is Zion. This is a collaborative work with Whitney, Zhao, who's driving the hardware part of this whole effort. And as you can see, any hardware co-design, or hardware software co-design, is a more interdisciplinary and a larger collaborative effort. So just to give a quick summary or an overview of what I'm going to cover, it's been mentioned quite a bit today and yesterday at the keynote, that AI is becoming very quickly the single most critical workload going forward in terms of driving compute platforms, right? And at the rate of growth of AI, traditional compute or traditional design methods are proving to be very inefficient and not working. Just because AI itself, having them as one workload is a misnomer. AI has a variety of requirements which keeps evolving, which keeps changing over time, making it very tricky to actually adopt these traditional approaches. The solution that we have adopted at Facebook, and we believe might be it might be the only solution, or it could be something different, is essentially looking at application-specific hardware software through co-design. And what we do for this and our rationale, I go through that in the context of the large memory training platform, which is Zion. Right? So this is essentially what I'm going to cover through. And before that, just to recap or motivate the need for having such a design or the challenges with AI training. So AI training, in some sense, essentially follows this pipeline where you have a lot of data, you extract features from this data, and you learn a model, which could be a neural network model or something else. You evaluate it on the metrics that you're interested in, and that's an iterative process. And when you hit the target metric that you're happy with, then it's deployed. So this whole pipeline, as you can see, it touches all different components of the infrastructure, right? If you look at the entire data center, it looks at storage, where you have petabytes of data which you're consuming to gather or extract information. The training and the evaluation itself has a lot of compute and memory requirement because you're churning through these large neural networks or deep learning models. And then deployment and even consuming these features has a lot of network requirements. So you touch all of the subcomponents, all the other parts of your infrastructure, making it a very challenging workload. While doing this, the users or the machine learning engineers demand flexibility and performance. This is kind of the key tenet, and you'll see this as an underlying theme when I talk about our objectives that we've tried to adhere to while we've talked through or designed through the training platform. And flexibility is also very important, especially for training, when engineers or researchers would like to actually try out different variants, given the fact that deep learning or AI is moving so fast, and being able to flexibly experiment and at a fast speed is very important, and it becomes a key requirement. While doing this, all the components are stressed, and if you look at the growth in itself, combined with both of these requirements, even the growth of such application is staggering, right? Misha had a more detailed breakdown in his keynote yesterday. Just to summarize, at Facebook alone, we've been seeing about a 3x growth over last year. And this is not necessarily only the compute, but also the data that's being consumed by training. And this doesn't necessarily mean that overall data has improved, but the amount of data that's consumed while doing a training operation has gone up by 3x. So we are able to consume 3x more data and extract some useful information out of it, right? And this growth, the issue is, and why we're looking at alternate methods, this growth it's not sustainable, right? You have such a challenging workload, you have requirements across the different subsystems, and it's growing at such a staggering rate. While on the other hand, the technology itself is hitting a wall and it's kind of slowing down with Moore's law slowing down, Dennard scaling, losing steam. You actually are not getting a lot from traditional machines or traditional computers. So this translates into this growth of the workload, needing to have prohibitively large fleet sizes, which becomes a no-no, and it's really hard to kind of sustain. So the solution is more smartly looking at the application itself, designing the hardware so that we can actually have hardware which are able to extract or leverage, exploit all the available potential for such applications, instead of trying to force fit this into a more general purpose solution. What's hardware software co-design? It's essentially, I mean, if you think about it, it's not something which is brand new or invented now. This has been around for a while, and it was pioneered way back in 2013 when IBM adopted this for their Blue Gene Q supercomputer. And in some sense, Blue Gene Q is very important because that was the first supercomputer where science applications or real-world applications were able to have more than 10 petaflops of sustained performance. So looking at an application first in a co-design manner, they were able to actually achieve not just benchmarks like HPL, but application-level performance of 10 petaflops or more. So what essentially entails co-design, right? Instead of trying to design just the hardware and software in isolation, we look at that in a more concurrent fashion. We look at the hardware, understand the software that we are going to run on it or the application, map it to that underlying hardware, and iterate through this, trying to say, look, here is how I can extract, and here are the knobs that we have on the software and on the hardware side to be able to fine-tune so that we can extract the performance. And these knobs themselves are quite a few. So if you look at the knobs in terms of software itself, there's the application level characteristics where I'll talk about it a little bit in detail. Even if you just look at AI applications, there are a plethora of them, and each of them having unconventional and quite often conflicting requirements. And then for each application, there's numerics and algorithms, the way you formulate that application or the task you're trying to do. They can be done in different ways. For instance, you can actually have a very scalable, large batch type of training, which actually has implications on the quality, but done right with learning rate and momentum and so on, you can actually get to the same thing. And the framework itself, which is particularly important for AI, and then the compiler, which helps map all of these applications and the kernels that you have to the lower level architecture. On the hardware side, there's the system itself, how you design this, and that's something that I'm going to talk about here at the Zion case, where we're trying to design a system. And we can go further levels down, as if you look at the individual compute element itself. For instance, if someone's looking at an inference accelerator, you could actually design that or specialize it for application-specific requirements, and going all the way down to device physics. And as you can see, it's a huge solution space, and it's easy to kind of say hardware-software co-design, but what it kind of entails or the details in it are quite large, and it can become quite complex. So to kind of peel the onion, go one level deeper, what I'm going to do is take an example of the large memory training platform and go through the rationale of what we followed through here so that I can actually motivate and explain better the high-level concepts of co-design. So stepping back, for any co-design application, I think the first thing is to identify the target applications that this is being designed for, understanding their characteristics, and going from there, trying to see what are the requirements and going further. So at Facebook, for us, there's a huge push on AI, and AI is used across various services. But if you look at it in terms of a very broad, high-level characterization, we have these three categories, right? Ads and recommendation, or ranking and recommendation, which powers their ads feed, which is the core business for Facebook. And also a lot of work on the computer vision, such as image classification, detection, video understanding, which plays into the integrity and the other sort of applications. And then you have language, where you have translation and content understanding. A lot of this, I think, was also talked about in detail at the keynote. But at a broad level, this is how we actually categorize these three sets of applications. And you'll see why when we go into the next level of detail as to the characteristics of each of these. So looking at the recommendation systems itself, which form a very core application class for Facebook, essentially they have a very unique set of requirements. The models themselves are very large, essentially made out of embeddings and fully connected layers, which are dense matrix compute. And you can see the model sizes are very different from the ones that are typically seen for the convolution neural networks or the language cases, which are more popularly studied and understood. So 10 billion essentially translates into hundreds of gigabytes in terms of the model size itself. And this is the deep learning model, not the amount of data that I'm looking at. And then another key characteristic is the operation. The last column here is essentially the op intensity. So it's given that these are sparse, bandwidth intensive with huge models, there's not a lot of compute. So this essentially is kind of an antithesis to a lot of work that is seen driving deep learning in terms of convolutional neural networks or RNNs, where you have dense matrix multiplication, a lot of compute. As you can see, these are used also in our applications. And you can see, for instance, a convolution neural network used for computer vision can have an op intensity of up to 22K. There's about 5 orders of magnitude in terms of range that needs to be catered for. And in terms of the model size also, you see a similar kind of diversity, right? So if I were to look at all of these and try to qualitatively identify what the requirements for a training platform are, in the 3 levels, again, recommendation, computer vision, and NMT, you can see the recommendation system kind of stresses out all the components and trying to push for what it needs in terms of requirements. The memory capacity is very high, very large models. And when training, you actually maintain the gradients and intermediate copies, so making it memory footprint even larger. The bandwidth is high since it's very sparse and memory intensive. And given these models are large, it's necessitated to actually split them across multiple devices, hence having hence making it very sensitive to interconnect bandwidth. The compute rate is something that's not high because you saw the operation intensity for this is lower. But then we have the computer vision models, which actually kind of push this even further, having high compute requirement. So if I were to kind of try to step back and say, if I'm designing a training platform for this classes of application, where do I actually look at and how do I gather requirements? So for the capacity, bandwidth, interconnect, and so on, I would actually look at the recommendation model for the requirements. And for the compute, as long as I provision it for compute for the likes of computer vision or the CNN models, then I have a solution which is sort of designed for the maximum case and would work for the plethora of applications that we have, right? In terms of, again, the key objectives being flexibility and performance. So since a lot of my talk next is going to focus mostly on the recommendation model, since this covers a wider set of requirements, just to step back and go back and look at what these are. I think this was also talked about at the keynote yesterday, but just to go into next level of detail, this is essentially what the type of recommendation model that we use at Facebook. I mean, we call it the deep learning recommendation model, or DLRM at short. So essentially, this combines categorical features, which are sparse features here, and continuous features, which are continuous numerics, through an embedding lookup to arrive at a dense representation, and then MLPs to kind of combine this and glean information about both the categorical and continuous features together, giving us a final prediction or a recommendation of some sort. So this essentially has, in some sense, the sparse features, which are large tables, memory capacity dominated, the embedding lookup operation, which converts these into dense vectors, which are bandwidth intensive, and then you have the MLPs, which are the fully connected layers, which are compute, basically matrix multiplication. And given that they're kind of split out in this particular way, there's the interaction, which has them bringing it together, and there's communication required. I would also want to say that this essentially, given that this is a very important application, we've written up a PyTorch version of this and open source it as a representative benchmark to allow the industry and people like you to actually go back, look at this, and to be able to reason about performance and the type of application that we're looking at. Given that there's been a lot of push towards convolutions and other type of networks, we thought it's interesting to have this a representation for this class of workloads, which are very important. So our solution, going back to what a Zion is, and I think many of you might already be aware of this, but this was introduced at the Global Summit by Vijay, talked about it. I think Whitney had a detailed presentation on it. But essentially, the Zion platform is a dense supernode design. We have 8 CPUs and 8 accelerators. And the 8 CPUs together give us about 1.5 or terabytes of memory capacity, and which caters to the large memory requirements of the recommendation model. And the accelerators provision for the compute requirements. So totally, we have about hundreds of teraflops or more of compute coming from the accelerators. And then the memory capacity being contributed by the CPUs up to terabytes. So we have this kind of more of everything in one very tightly coupled box. Given that we have this in kind of a 8 accelerator, 8 CPU setup, the interconnect between them becomes very important. So we have 2 separate high-speed interconnects between the CPUs themselves. There's an UPI link, which enables low latency, reasonable bandwidth interconnect, and then there's an accelerator fabric, which is a high bandwidth across those 8 accelerators. The benefit here, if you go back to the model that I was talking about, large recommendation models, which you split across the 1.5 or terabytes of memory that you have, then you would essentially need to have this low latency, fast communication between them to be able to exchange the data that's split across. So that's how this is provisioned. And this is kind of a snapshot of one box. And if we were to look at these models as catering to large training work systems where you want to scale out, that's also provisioned with 800 gigabit NICs. So if you were actually bringing in a lot of data or scaling out to multiple nodes, we have enough network bandwidth. So this is, in some sense, the snapshot of our solution. Now, stepping deeper and trying to understand why we came up with this and what's the rationale behind this, right? So the Xeon system there was a schematic diagram. If you look at the actual system, it's designed in kind of a modular way. You have 2 subcomponents, one which is the Angel's Landing, which is a CPU subcomponent, and the Emerald Spool, which is the accelerator component, which houses the OAM. And both of them together makes up the Xeon system. So if you look at it from a very high-level view, the CPUs map really well to the sparse and the memory bandwidth-dominated applications. And then the accelerator piece is to cater to the MLPs, which are mostly dense matrix compute. And this looks very nice when you look at it, and it seems like, oh, this is a very nice partitioning. But the devil is actually when you get into the details. For this simple kind of a markup, when you actually go under the hood and map this out, this is how it becomes. This is the mapping that you would end up with, right? One candidate mapping. So here, as you can see, this becomes fairly complex. I'm showing a picture of, say, one possible case where you have 4 nodes where you're splitting the embeddings, and the remaining 4 you're splitting the MLPs, right? So the embeddings themselves, which are essentially your model, are partitioned across the 4 to cater to the capacity requirements. And then you have the MLPs, which are much smaller, but you want to be able to leverage all the compute. So you're going to be, you would typically want to split this based on sample. So you would do a data parallelism across the MLPs. Given this kind of a model plus data parallelism hybrid solution, the communication pattern becomes quite complex, right? You have an all-to-all where all the embeddings from the first 4 have to be communicated to the MLPs, and then they can proceed. So if you go back to the picture on the top right, so you have the embeddings. The results of the embeddings are interacted, and then they're fed to the MLP. So the embedding lookup needs to happen. The results need to go to the MLP, and then we can proceed. So you have this all-to-all for the embedding because they're parallelized across the model. And since the MLPs themselves are parallelized in a data parallel way, they're replicated given they're smaller. Since when you train, the gradients that you achieve on these have to be synchronized and reduced before proceeding to the next step. So there's an all-reduced type of an communication happening across the MLPs. So the key, we talked about flexibility and saying we have an OAM-based module and the accelerators cater to the MLP. The immediate question that comes up is when this is still interconnect or network interconnect sensitive. And when we have a generic solution like the OAM, where we are trying to be able to be, where we are trying to be vendor agnostic, and we saw AMD and NVIDIA having their OAM modules, and there's the Habana one and the Intel that's already been demoed. So we want to be able to plug and play or use different accelerator solutions. And given that it's also interconnect being an important part, the key question is, with all of these accelerators, how do we make the interconnect, which is an important piece for the MLP, to be generic also? And one of the key kind of innovations that came out, which is part of the Emerald Spool design, is on the baseboard, we actually have a fully connected interconnect topology. But to be able to cater to alternate topologies offered by different vendors, you can actually transform that by removing links and swapping it out into a hybrid cube mesh, which some of the vendors actually cater to. So this gives us a sort of a superset. And it also caters to the requirements of the communication primitives, where we have both all-reduce and all-to-all. So staying in the theme of flexibility, flexibility in terms, as I mentioned, I just want to recall, one of the key objectives or requirements for training is having flexibility, and flexibility in terms of hardware and software. If you recall, we had a long list of applications having different requirements. Although the 8-socket, the 8-accelerator module caters to the recommendation model type of applications. If we go back to the CV, which are more compute intensive, the 8 CPUs are somewhat wasteful, right? Having that type of capacity is not necessarily useful. You burn power and it kind of reduces the efficiency. So to be able to cater to this, I think one of the key things that we've incorporated into the Xeon design is to make it modular. It's 4 2-socket modules which are kind of identical. This allows us to reconfigure this, having the 8-socket system, 8 CPU as the full-blown thing, and then a 2-socket 8 CPU to cater to the more compute-intensive workloads like CV or anything in between if you were to have machine translation, neural machine translation, or other language-based workloads. So this flexibility allows us to cater to different applications without loss of efficiency. Right? And not just flexibility in hardware. So we would essentially need to have this flexibility in terms of software also. Given that experimentation and fast experimentation is a key requirement for training, and it's an important requirement for success, this kind of a supernode design allows us to create a continuum in terms of developing or having software. So the first cut, an engineer trying to try out a very simple model that he has in mind, he thinks it's the greatest idea, he can just write it up very quickly on the CPU, not with minimal effort, try it out, but you're not going to get a lot of performance. But given that you have so much memory that's available, you should be able to try out fairly far out models to test out hypotheses and experimentation. Once there are several iterations of this where you've tried out and the engineer is fairly confident, then investing more into each level of optimization, whether now I try to push the compute-intensive part onto the MLPs, onto the accelerators. And then I also take and there's also HBM on the accelerators, which gives you significant bandwidth. And then the next level of optimization could be that you actually take the memory bandwidth-intensive parts and push it down to HBM. So seeing further gains as you go along. And then, depending on your application needs, take it all the way to training multiple of these nodes. So this provides kind of a nice continuum to be able to try things out, where you can quickly try something out on the CPU with reasonable performance, and depending on how far along you're on your experimentation, further invest into the software to glean or get more out of in terms of performance. So now in terms of performance, a key requirement, although this is something that we're designing, we're testing out, we don't have it completely deployed, but a key requirement when we talk about designing or co-designing any system is to be able to reason about what is the performance benefit we expect, why we are doing a certain case, why 8 is a sweet spot, why we would want this sort of compute, and so on and so forth. And having a performance model, given that the hardware is still being built out, is very important. And making sure that there's enough fidelity in the model itself, whether through benchmarking or through roofline modeling, it would be very important to be able to make some of these choices. And to just give a snapshot, I'm not going to go into full detail, I'll be happy to take that offline, but to give a snapshot compared to what we have in terms of a distributed training setup today, using up to 32 or more nodes, a single Xeon system, spec'd the way I talked about here with 8 CPUs and 8 accelerators, can get up to about 2.5x over 32 distributed nodes. That's kind of the value proposition. Again, this is at different levels. If you were to do only 8 CPUs, you're not far off. You're about 50% on a single box compared to a distributed setup. So there is still a value proposition to be had for faster experimentation. And then you move to the 2.5x case where you're trying to extract all the juice that a single box can provide. Why do we get this 2.4x? And if you go back and look at how the key thing what we've tried to do here is to balance out the bottlenecks. So if you go back to the distributed case, you can see there's the dense communication and the compute start becoming some sort of a bottleneck. And you typically scale out and then start hitting the network bottleneck, which is clearly seen on the baseline case. So what the Xeon tries to cater to or tries to do as a design point is to balance this out in a single node setup, having enough compute so that it doesn't become a bottleneck while other components are also commensurately proportioned. So you can see a more balanced split that kind of translates into the 2.4x benefit. So for instance, if we were to add more compute, here you would see that it's actually giving you very little in return. So the compute goes down, and you're not seeing an overall benefit. So making sure that it translates into application level performance benefit is a key requirement, as a key objective when doing such a design. So to kind of conclude, so AI is never seen in isolation. It's part of a larger distributed service. So looking at the end-to-end application through all the components, not just focusing on just the gem or the compute alone, the data being brought in, the feature preparation, which is more memory intensive, and scale out becomes a very important consideration to have. And focusing squarely on just one node or one GPU, getting the most out of that is not going to be translating into full application level performance. And again, this is a point that I think Misha made also very nicely with the numbers that he had in the keynote. Essentially, focusing on dense, regular matrix multiplication is not sufficient. There are such applications like DLRM, which are very widely used in industries, which are trending towards more unstructured, irregular, and more memory-intensive application. And when looking at anything to do with training, programmability, flexibility is very important. Faster, while not trading off on performance, so that there is faster turnaround times on experimentation, which enables success for any such platform. That's all I had. And call to action, please take a look at our DLRM GitHub code. Take a look at it. Any questions you have, this is representative. I think we would love to foster more work in the wider industry. And if there are other potential candidates or use cases for Xeon from different parts of the industry, we'd love to hear more and see how we can map these things to the Xeon type platform. Thank you.